So we have Physics Ph.D. practice qualifying exam problem number 13 in electricity and magnetism. So let's begin. A charge undergoes harmonic oscillation. X of t equals a cosine of omega t with non-relativistic velocity. For part A, derive the far zone electric field. Part B, derive the magnetic field. Part C, determine the angular power distribution, the derivative here, this P, derivative of P with respect to a capital omega. Part D, calculate the total radiated power. Part E, compare this with the Larmor formula and show consistency. And here, part F, determine polarization of radiation observed at an arbitrary angle theta. Okay, so let's see what we can do here. Radiation from an accelerating charge problem, part A. For deriving the far zone electric field, the charge moves as x of t equals a cosine of omega t, where v is much smaller than c. So r sub q of t equals a cosine of omega t x hat, and our velocity v of t equals negative a omega sine of omega t, and that is times that x hat. And then our acceleration, a of t equals negative a omega squared cosine omega t of omega t x hat. The non-relativistic assumption gives that a omega is much less than c. And for a non-relativistic accelerating charge, the far zone radiation electric field is E sub RAD of R comma T equals Q over 4 pi epsilon naught C squared R n hat crossed with bracket n hat cross A T sub R bracket. Okay, so substituting for this A T sub R, that equals negative a omega squared cosine of W T sub R x hat. So we could say this E sub RAD equals negative Q A omega squared over 4 pi epsilon naught C squared R cosine omega T sub R n hat cross with this in parentheses n hat cross x hat. And if we use the identity, n hat crossed with parentheses n hat crossed x hat, that equals n hat parentheses dot product of n hat and x hat, close parentheses, minus x hat. And the field is transverse. Dot product of n hat and E sub RAD equals 0. So we could say its magnitude here, E sub RAD equals QA omega squared over 4 pi epsilon naught C squared R, and then times that absolute value of cosine of omega T sub R, and then times that sine theta. And this is where theta is measured from the oscillation axis, the x-axis. Okay, so that's letter A. And for letter B, they want us to derive the magnetic field for letter B. So let me just change this. Sorry about that. So here for letter B, magnetic field in the radiation zone B sub RAD, that equals the following 1 over C, n hat crossed with E sub RAD. So B sub RAD, that equals E sub RAD over C. And E sub RAD, B sub RAD, and n hat form a mutually perpendicular right-handed triangle. Okay, so that's for letter B. For letter C, they want us to determine the angular power distribution. So the angular power distribution, the Poynting vector is S equals 1 over mu naught E sub RAD crossed with B sub RAD. And since B sub RAD equals E sub RAD over C, the radial power flux is S sub R equals epsilon naught C, E sub RAD squared. And the power radiated per solid angle is that derivative of P with respect to capital omega equals R squared S sub R. So using here this E sub RAD squared, that equals the quantity QA omega squared over 4 pi 4 pi epsilon naught C squared R, that quantity squared, and then times cosine squared of cosine squared of omega T sub R sine squared theta. So we get this derivative here, dP d capital omega equals R squared epsilon naught C, and then this quantity Q A omega squared over 4 pi epsilon C squared R squared cosine squared of omega T sub R sine squared theta. So therefore the instantaneous angular distribution is this derivative of P with respect to capital omega equals Q squared A squared omega to the fourth over 16 pi squared epsilon naught C cubed cosine squared of omega T sub R sine squared theta. And equivalently, since A of T sub R squared equals A squared omega to the fourth cosine squared of omega T sub R, dP d capital omega equals Q squared A squared T sub R 16 pi squared epsilon naught C cubed sine squared theta. Okay. That's for letter C. For letter D, calculate the total power radiated. So the integrating over the solid angle here, this P of T equals integral there of dP d capital omega d omega. And since the integral sine squared theta d omega equals this setup here for this integration, 0 to 2 pi d phi, 0 to pi sine cubed theta d theta, that equals, when we compute, 2 pi times 4/3, which is 8 pi over 3. So P of T, Q squared A squared omega to the fourth over 16 pi squared E naught C cubed, cosine squared of omega T sub R 8 pi over 3. So P of T equals Q squared A squared omega to the fourth over 6 pi epsilon naught C cubed, cosine squared of omega T sub R. And the time average over one cycle is going to use cosine squared of that omega T sub R equals 1/2. So this P of T is going to get cut in half to give this time average here. Q squared A squared omega to the fourth over 12 pi epsilon naught C cubed. Okay, so moving along to part E. Part E, compare this with the Larmor formula and show consistency. So the Larmor formulation in SI units is P sub Larmor equals Q squared A squared over 6 pi epsilon naught C cubed. So this A of T squared equals A squared omega to the fourth cosine squared of omega T. So P of T equals Q squared A squared omega to the fourth over 6 pi epsilon naught C cubed cosine squared of omega T. Averaging over time, we get 1/2 A squared omega to the fourth. So we're going to wind up with Q squared over 6 pi epsilon naught C cubed 1/2 A squared omega to the fourth. And we wind up with Q squared A squared omega to the fourth over 12 pi epsilon naught C squared when performing the computation there. Okay, so letter F, determine polarization of radiation observed at an arbitrary angle theta. So here's letter F. So the radiation electric field is proportional to n hat crossed with parentheses the cross product of n hat and x hat. close parentheses here. This is the component of the oscillation direction x hat perpendicular to the observation direction n hat. Equivalently, E sub RAD is proportional to x hat minus this, in parentheses, the dot product of x hat and n hat, and then close parentheses n hat. And the radiation is linearly polarized along the projection of x hat perpendicular to n hat. And along the oscillation axis, theta equals 0, so sine of theta equals 0. So no radiation is emitted along the axis of oscillation. Perpendicular to the oscillation axis, theta equals pi over 2, and the radiation is maximal. Okay, so that's all for this problem. Thank you very much, and have a great day.